Hi, welcome to the Signal Path. In this episode, I have another product review for you guys. We'll be taking a look at the Rigol DSA875 spectrum analyzer. This is a 9 kHz to 7.5 GHz spectrum analyzer, and if you've noticed, 7.5 GHz is an unusual end frequency. Normally, spectrum analyzers like this end at 6 GHz, and this is a big advantage because it gives you access to the third harmonic of 2.4 GHz signals. Under some conditions, it can be useful. Not always, because a lot of times the PAs that you'll use at that frequency range are quite bandwidth limited. But if you want to use it for pre-distortion or looking at third harmonics at higher frequencies, this can be a huge advantage. It also has a built-in tracking generator. You can see directly over there, and that is also a huge advantage because it gives you a full 7.5 GHz tracking generator capability. It can also do quite a few different types of measurements already built into it, so we'll take a look at all of that. It has about 100 dBc per hertz of phase noise at a 100 kHz offset at 1 GHz, which is not too bad. And again, for something this size and at this price, about $9,500 is pretty reasonable. So it's quite a competitive unit, and I have a whole bunch of experiments set up, but first we'll take it apart, take a look inside it, just a brief overview, see how it's manufactured and how the quality of the build quality and the engineering that's gone into it before we get into the experiment. So let's get started. So let's take a look and see what's inside this unit. Now I've taken the back plastic piece off, which there was nothing really exciting about that, and it of course hides the isolation and the chassis design of this unit. And look how incredibly nice it is. It is completely and really well isolated from all angles. It encloses everything that's inside it. The only thing that really sticks out is the power cord over here, the power plug, which also is fully enclosed, as you can see, in this cubic structure of metal. Very nicely done, and all the trigger and the 10 MHz outputs, of course, as well as Ethernet and USB. So they've really figured out how to do this in a nice way. I have to say, it's there's really nothing wrong with it. In terms of thermal design, the fan is on this side, and it either blows air or sucks air in this way, and it passes it through this structure. So by the shape of this, we would expect that the power supply be all the way up here against this chassis, so that all the microwave components and the boards will be inside. So I've taken the screws all around it, and I hope and I think it should come out. There we go. Oh, something's holding it down. Oh yes, there it is. And check it out. Look at this. I mean, this is exactly the kind of design you would expect from something like this. Let me get this power supply cable out, if I can. I'm in a really awkward angle here. Let me get this, unplug this, and we'll come back. There we go, success. I disconnected the connector. Now this is the only interface between this portion, the power supply, and the main board is through this connector over here. Even the fan runs directly from the power supply module. And this is a very nice design because this allows complete isolation from the power supply to the unit, of course, and this is also nicely thermally designed because the fan blows air and there's plenty of space over here for the air to go back out. You can see the main lines coming in, and they're nicely tied down, shrink tubed on the inside of this cavity over here where the main power comes in. Now the edges of this edge over here is very nice and smooth because it's folded over, but these edges are not. They're actually quite sharp, and this wire can just rub against this and ultimately cause a problem. So I'm gonna probably tie these together myself just so I can protect it in this unit. But I would probably suggest maybe tying this down somewhere or making sure that it doesn't ultimately cause, because if this gets cut, this is the main live wire, then it can be quite bad. But other than that, looks really nice. The power supply is some generic power supply. I'm not going to take it apart, there's no need to. But you can see that they've gone through quite a bit of trouble to make this chassis. Nice thick walls everywhere. They've really figured this type of design down. This is not the first time they've built this form factor. This was from before when they had the 1.5 GHz units and the 3 GHz units. So they know how to build these for sure. So I'm going to put this aside, not going to dwell on this too much anymore. But here's the main board, and just take a look and see how beautiful it is. And if you ever saw this and you didn't know where it came from, your first guess most likely would not be a Chinese designed, Chinese manufactured company. This shows that how much they have advanced in terms of producing what is essentially indistinguishable, at least at first glance, from the designs you would say from Keysight or Tektronix or even Roden Schwartz. So they've put clearly quite a bit of effort in there. Really nice microwave design. They have two stacked boards to make it obviously more compact. The boards are separated by this custom aluminum machined pieces, which is of course for isolation. You've seen this before in any of the other instruments that I've taken apart. All the digital section over here fully isolated again, and you can see that the interface between this top board and to the PCB, there is a board-to-board RF connector there, which is very nice. You can see the PCB sticks out of underneath this chassis piece here. So really nice design. I mean, I'm sure Keysight and Tektronix and Roden Schwartz, and they're taking note of the fact that these things have become so good and so similar to their own design. And I mean, after all, the manufacturing process of all the Keysight and so on, they manufacture their stuff overseas anyway. So this is the same manufacturing process, except that this is also now designed as well by them. So very nice to see quite a bit of competition in this space. So let's take a little bit closer look at some of these components. I'm not going to completely take it apart because I want to do the experiments, but we'll take this top piece off. I've already taken the screws off, so we can take a look inside. And this top portion over here, judging by the connector going into it and the two custom cables that are coming out, likely maybe the synthesizer portion of the whole thing. I think that the final IF section is probably coming out over here, but anyhow, we'll have to take a closer look and we'll take this off, and you'll see probably a bunch of microwave design underneath it. So should be pretty cool. So here's a look at all the digital section. Obviously the USB Ethernet connector. This is the ribbon cable that connects all the switches and the keyboard pads and all that in the front, and this is obviously the driver all the ribbons that drives the LCD screen. There's a Spartan 6 FPGA clearly driving the display directly from the Spartan FPGA. There's an Actel processor here. There's a Pro ASIC 3, actually has a Cortex M3 ARM processor inside it, so it's got quite a bit of kick to it. There's a Cypress USB controller and a peripheral controller over here. There's some flash memory there. There is a Blackfin analog devices processor over there, a whole bunch of different kinds of memory, some DC-DC converters, and there's a component over here which actually has been kind of cleaned off, so you can't see the part number. They have completely machined off that piece. It's clear that it's not done by hand, it's done in some kind of an automated fashion because of its clean edges and so on. And I'm not sure what that part is, but judging by where it is, it could be the final analog to digital converter they use in the final IF converter by its proximity to the FPGA and by its proximity over here. Maybe that's what that is, or could be the synthesizer IC. I'm not quite sure, but either way you cannot see it. Interesting heatsink over here. So whatever is on the other side of this board probably needs some extra cooling. So you can see that very straightforward in the sense that they have really thrown quite a bit of processing power at this machine to get everything later software configurable, which is nice in some ways. Makes it quite configurable, and this is obviously the battery for the to keep all the BIOS settings and so on, and there's the power connector over here. So pretty nice, I say. You can see the soldering is very nice. There's no mistakes in it. Very, very clean, nice board, nice gold plated. Everything looks really good. We can also take a look at what's underneath this board. This piece of metal over here, and there it is, as we were expecting. Obviously a whole bunch of different microwave design over here. There is another Xilinx Spartan FPGA over here, some power management circuitry, and you can see whatever is connected through here is likely going through this board and then connected to this board. I'm guessing it's maybe the synthesizer portion, because this thing does have a tracking generator, so they have to do all of that. You can see various filter structures. There's a coupler over here that you can see, directional coupler there. There is a whole bunch of other different ICs for amplification and filtering and so on. Again, I'm not going to go into too much detail, but the main point I want to get across is, it looks very nice. It's exactly what you would expect to see if you were to open any high-end instrument. And interesting, you can see slits that they have designed into the board here. Obviously these slits are not for the same purposes of the slits that you see in high voltage boards. These are for isolations and so on, different reasons to make sure that you don't get resonances in the board. I'm not exactly sure what these pads are for, but that's likely what they're doing. Other than that, very, very cool. I'm very impressed by the design. I wasn't expecting to find something basically world-class in terms of design, at least from the way it looks. Now, in terms of performance, obviously this unit doesn't meet the performance that Keysight, for example, offers, but then the Keysight instruments are also quite a bit more expensive. So, and this is really, really compact, so that has something else to keep in mind. Well, I'm not going to go any further in this. I'm very much interested in showing you the experiments. I hope at least you get a rough idea of what it looks like on the inside in terms of its build quality. I'm quite happy with it. And here's the front panel of the DSA875 from Rigol, which is a 9 kHz to 7.5 GHz spectrum analyzer, as I mentioned. And you can see that the unit is actually quite small. It's very compact, and I like that it fits almost anywhere in the lab. It also has a very small depth, as I will show you. So Here's, for example, compared to my phone, right up against it, so you can see it is a pretty small and compact unit, great for moving around in the lab. Most of this unit is obviously occupied by the LCD screen, and one of the things I love about the LCD screen is that it has a matte finish. It's not reflective at all. You can barely see my reflection in it, even though there is very bright light shining on it. And this is really important. I wish more manufacturers, including Keysight, would recognize the importance of having a matte finished LCD, because it in a really bright lab environment where you have big ceiling lights on there, if you're sitting at an awkward angle, all you're going to see are the lights in the ceiling, and this can be very frustrating when you're trying to do measurements. So I really appreciate that the LCD screen looks really nice, especially also when it's turned on, as we shall see. Now the front is divided into a section for all the buttons, of course, and you have the tracking generator output and the RF input right over here. Both of them are 50 volt maximum rated. Of course, that means that they're AC coupled internally, and especially you can know because the unit starts at 9 kHz. Now, one of the things to watch out for is that the RF input, which is of course 50 ohm in the Rigol DSA875, is rated to a maximum of 20 dBm. Now that's not very much. 20 dBm is 100 milliwatt. It's really easy to exceed, and most of the time spectrum analyzers are rated to 30 dBm, to 1 watt. So you have to be careful, which means that if you're going to use this, especially for things like Wi-Fi applications and so on, where you may have PAs that put out more than 30 dBm or could put out more than 30 dBm, you want to have some attenuators handy in order not to damage the input of the spectrum analyzer. And we can see how it handles overloading as well. On the left, you have a couple of buttons for preset and help and so on. You have a recessed power on button, which is a soft power on button, the USB port, and a headphone jack out for the demodulation to listening to the sound from there. You have soft buttons here, which is very typical with the Rigol instruments. They all have this, and of course contextually connected with the return and the down button here. And all the other buttons are separated into control markers, measurements, utilities, and edit. And of course you have frequency, span, and amplitude. So this layout is basically almost a replica of any other spectrum analyzer from Keysight and so on. This is a very logical distribution of buttons. These are the buttons you would expect to find. Of course, you also have the tracking generator, which can light up, as well as the measurement button and an auto button. I don't know why the auto button has to have a light behind it, but anyhow, it does. The tracking generator light is important because it will tell you that something is coming out of the tracking generator, so you can watch out for that. I don't think anything else needs a light, but it's convenient to have those for some other functionality. This rotation knob is okay. It doesn't have the greatest feel to it, but it does work reasonably well. The buttons have some freedom to them, but I've never had any problem with pressing them. I really like the color scheme, just simply because this just happens to be my favorite color. But other than that, very nice, very compact, very well built. It just feels full. It's very heavy, and we will take it apart and we'll take a look inside it. So far so good. Let's take a look at the back. And here's the back of the unit. No complaints there. We have the power plug, of course, here. You can see that it says Rigol Technologies, made in China, and it accepts 100 all the way to 240 volts. No problems there. Here's the lock at the back, and on this side, which I will turn the unit maybe a little bit so you can have a better look, you can see that you have the USB device, Ethernet, which is all standard as it is with all of Rigol's instruments. Fantastic, putting pressure on the competition, providing all of these as standard. I love that. And then you have the trigger input, 10 MHz output, and 10 MHz input, and we will take a look at all of those as well. It kind of looks like a spaceship from the back with these big indentations in it, but like I said, very compact. Just look at how small the dimensions of this unit is. You can see a fan over here, and we will have a closer look once we take it apart. But I honestly can't find anything wrong with it, and the carrying handles are obviously up here as well, and nothing wrong with it from the perspective of construction here. It looks really nice. So next thing is, of course, turn it on, do some measurements with it, and put it through some tough tests. Now, with Rigol releasing a 7.5 GHz spectrum analyzer like this, which is an unusual end frequency, as I talked about before, they're really targeting people to use this for all the ISM bands, and even for pre-distortion as well as linearization techniques and so on, because you have access to the third harmonic now. It would be very interesting to see what it can do. Now, as with any spectrum analyzer or any high-end instrument, software is key. You have to make sure the software can deliver on all those things, and they have developed proper applications. And as I go along, I can make suggestions of what I think would be very useful to have added to this instrument. So let's go ahead, turn it on, and see what happens. So let's go ahead and turn it on. Now this is a soft power switch, as I mentioned, and of course it runs an embedded operating system. Now I have updated the firmware already to the latest one. Now for an embedded system, it boots actually pretty quickly. Now we're just about 15 seconds. It will decompress the firmware and then do some device initialization. It will not do an initial alignment. It only does alignment when the temperature changes or when it detects that it needs a new alignment. So now there you go, we're just at 25 seconds and you can see that it boots pretty quickly. So I'm fairly happy with that. Now I'm not going to go into the details of the GUI very much because we're going to see it through the different experiments, but I do like the GUI of the instrument here, especially this little display on the side here which shows you the status of the unit, so you can quickly glance at it. For example, it's doing peak detection, it's a free running, continuous sweep and so on, and these things will light up as they become enabled and disabled and so on. So I like that. Nice and clean display, but one of the very first things to notice is how fast it actually sweeps. This is a huge improvement over the 1000 series spectrum analyzers that I reviewed before. It's actually comparable to the best in the industry. It sweeps from 0 to 7.5 GHz in 37.5 milliseconds, which is great, and this will allow you to catch spurious events more frequently. Now if I were to go ahead and reduce the bandwidth from 1 megahertz to, let's say, 100 kilohertz, then it will slow down to 750 milliseconds, which is quite a degradation. But once you go to 10 kilohertz, then it becomes really slow. Now we're looking at a 75-second total sweep time, and the displayed average noise is just above minus 90 dBm. At the default 1 megahertz, the display average noise level is about minus 70 at lower frequencies and minus 60 at higher frequencies. But I'm very happy with the sweep. Now, one of the things the old unit didn't do very well was that it was very bad at detecting overload inputs. And what it would do is that the signal, once it exceeded the displayed limit here, the 0 dBm reference level, then it would just create a whole bunch of harmonics, and it wouldn't tell you that the signal at the input is in an overload condition. And that was really, really annoying, and it can actually cause you to make mistakes when you're doing measurements. So I'm going to go ahead, put a tone in there, and we're going to try and see what it does under an overload condition. And I'm going to also try and putting a two-tone in there so we can see if the intermodulation products degrade as it gets close to the reference or not. Now I'm going to show you that setup in a second. But this unit actually can measure the third order intercept points, and it has a whole bunch of other measurement functionality built into it, and we will take a look at all of those when I do the different experiments. So let's go ahead, take it one step at a time. Let's try the overload condition first. Now in order to investigate the IM3 degradation of this instrument very close to the reference point or any other degradation that we're interested in seeing, we don't want to connect the instrument directly to a synthesizer, because if you do that and you try to change the output power of the synthesizer itself is going to have degradation when it produces larger output signals. So we want to avoid that. So instead of doing that, I'm running the synthesizer through a mechanical attenuator first, so we can change the output amplitude, and the signal that's arriving to the spectrum analyzer, we're going to change its power by a mechanical attenuator which has essentially an infinite OIP3s, completely linear, at least for these levels of powers that we're dealing with. And that's going to be different from changing the attenuator of changing the power from the synthesizer directly. So let me just show you what that setup looks like. I'm sorry, I'm going to take the camera out and do a handheld here because I want to make sure that I shoot this nicely for you afterwards. So the signal is going to come from this synthesizer here. This is an Agilent or a Keysight EXG vector signal generator. It's going to generate starting from a 1 gigahertz signal. Its power is set to 20 dBm. And it's going to generate two tones for us, so we're going to look at the two-tone impact, and the tones are separated by 10 megahertz. And the output of that goes into this Anritsu programmable attenuator, which can go all the way up to about 80 dB or 85 dB of attenuation, so we're going to have no problems there. Right now it's set to 20. So if we have 20 dBm from the synthesizer, and then we have 20 dBm attenuation, so we're looking at as 0 dB power, but when it's generating two tones and you include the cables, it's going to be a bit less than that. So let's go ahead and put this camera back here, and I'm going to go and enable the output signal coming from the synthesizer, and let's see what happens. So I'm going to enable the output, and here it is. There you go. Let me press escape to get rid of that text over there, and here's our fundamental tone, and here's our second harmonic, and this second harmonic is coming from the synthesizer itself because it's producing 20 dBm and it's not going to be perfectly linear. Nonetheless, you can see it has a very good THD. Now let's go and do a peak search there, and you can see that the marker is now reporting 987.5 megahertz, which is fine because we're looking at the signal on a 7.5 gigahertz span. And remember, this is two tones, so this is going to Now, you're not going to be able to see the two tones because the resolution bandwidth and the span is quite large, and it's reporting a power of -5 dBm, which is also correct. So now let's go ahead and increase the signal and see at what point we're going to get a degradation. Now remember that the second harmonic and the third harmonic, which is tiny, these are going to slowly come up, and they have to come up 1 to 1 with respect to the fundamental, because this is a linear circuit here, and we're at -5 dBm. Let's go ahead and see what happens. So there you go, -19, 18, 17, 15, there you go. Now we are at officially -0.5 dBm. Now we are over 0 dB, so we are just over the 0 dB reference line that we have here. Still nothing. -13, now 1.5 dBm. And there you go. You can see that now we are at, the signal is now grown and actually shifted, so the marker is no longer on the signal. That's why it's saying -44 dBm, and it makes this really annoying beep sound and a pop-up on the screen telling you that your signal has experienced an overload condition, which is great. This is exactly what you want to see. You want to make sure that you're not over your reference level. And to show you that this is indeed a two-tone test, we can go ahead and go under frequency, and we're going to set the center frequency to 1 GHz, and we're going to change the span, lower the span until the two tones reveal themselves, like that, and I'm going to change the resolution bandwidth here, so we can get a little bit nicer, lower noise floor. So there you go, you can see very well the two tones. Each tone is at about -5 dBm. Here's our intermodulation products on each side, and here's the LO tone in the middle. I haven't run a calibration on the vector signal generator, so it doesn't have a very good LO rejection right now. Still has quite a bit, maybe 1, 2, 3, 4, about 40 dB or 45 dB or so. So it's pretty good still, but it can even be lower than that. So now, having said that, let me show you one other thing that I noticed, that this must be a software bug, and I hope that's something that they can resolve. Now look at this display update right here. You can see that it's saying that the sweep time is 5 milliseconds, and I have a marker, it's displaying the marker, and it's reading the value. Now I'm going to go ahead and turn the marker off. Now look at what happens to the display update rate. You see how it speeds up so much, but the time doesn't change. It still says 5 milliseconds, and as soon as I do a peak search, you can see that it slows down in the number of waveforms it's displaying. So I imagine that's because it has some extra processing time dedicated to picking up the peak value and running some mathematic computation on it. But it'd be nice if they can fix that so that you don't see such a degradation with the marker coming on. Now let's go ahead and increase the amplitude and see the overload condition again. You can see that the intermodulation products and the LO and the main tones kind of increase 1 to 1 with respect to each other. And here we go, here's our out of range signal, and it does exactly what it's supposed to. And of course you can always go ahead under amplitude and change the reference level by another 10 dB. So now our reference level is at -10 dB at the top, so the attenuation value jumped to 20 dB. Now we can have larger signals, and I can go ahead and go all the way this way. I can go all the way there. Then I can see that if I go under peak, you can see that it's now at 10 dBm and no overload condition. So it all is nice and great. Major improvement over the old version. So the next thing is, now that I just wanted to show you a very brief view of this overload condition because I knew it was important to you guys, but next is to jump and do some characterization on some actual components and do some extensive testing. The DSA875 also comes with a tracking generator. Now I have connected a type N to SMA connector to it right here, and the tracking generator has had some improvements over the old version. So if I go under the TG, tracking generator button right here, you can see that I can now adjust the tracking generator output level anyway from -40 dBm all the way to 0 dBm, which is great. It means that it can support a really large dynamic range of devices that you can test with it. For very high gain amplifiers, you do want a very small signal, and for passives you want a very large signal. So it's very nice to see that it has 40 dB of dynamic range. I'm also interested to see how clean the tracking generator output is. Now normally when you're feeding it back to the input, you don't care too much about the harmonic performance or the spurious performance of the tracking generator because the instrument mostly ignores and filters whatever is outside of band unless they're very, very bad. So you don't really care so much. But if you're going to invest in something like this and you're going to get it, and the fact that it goes up to 7.5 GHz means that the tracking generator goes up to 7.5 GHz. And if it can produce a reasonably good signal, then you have a synthesizer that also works to 7.5 GHz, which is fantastic because you can put the instrument into zero span and use it as a synthesizer also. And that's what I'm interested to find out before I do any tests with it. So let's go ahead, hook up the tracking generator output to a spectrum analyzer, not to this one of course, to a different one, and look at its performance and see what we get. There you go, I've connected the output. It goes right in front of the screen to a different spectrum analyzer. It's actually going to a Keysight spectrum analyzer. Let's go ahead and take a look. Now I'm going to set the tracking general level to 0 because I'm interested in seeing the highest output power, which will be the toughest test, because I want to get the most out of the synthesizer. So let's see. Alright, so we are looking at the screen of the Keysight spectrum analyzer. Right now nothing's enabled, so I'm actually sweeping from 0 Hz all the way to 7.5 GHz to match the spectrum, the Rigol spectrum analyzer. And by the way, just as a note, this is on a resolution band of 100 kHz and the sweep speed is 24.4 milliseconds, which is quite fast. So anyhow, so let's go back and I'm going to go under the tracking generator. Now everything is disabled. I'm going to go and increase the tracking generator amplitude to 0. And you can see that even though the tracking generator is disabled, there is some spurious tones that it generates. So it can't turn itself completely off. But remember, these tones are really small. They're below -50 dBm, so I wouldn't worry about it. Now, of course, these tones are going to move around because the instrument, the Rigol spectrum analyzer, is sweeping. So it's generating a tone that's continuously going from 0 to 7.5 GHz back and forth. So let's go ahead and change the instrument, the Rigol, to produce a center span. Let's say start from 1 GHz. I'm going to set the frequency to 1 GHz. I'm going to change the span to 0 span. Now as soon as I do that, then the spectrum analyzer is not sweeping the frequency anymore. It's measuring versus just time. So now it is at 1 GHz with a span of 0 Hz. Now I can go ahead on the tracking generator and I'm going to go ahead and enable the output. And check it out. Here's our 1 GHz tone. And you can see the other harmonics. Now, you also notice that occasionally it produces this spur, and I think it does that when it reaches the end of the time that it is doing the 0 span of. So right now the instrument is set to do a 10 millisecond sweep, and then it's going to continuously display that. So instead of 10 millisecond sweep, I'm going to change the sweep time to something much larger, let's say 10 seconds. If you want to use it as a synthesizer, that's what you'd want to do anyway. So let's go ahead under sweep and change it to 10 seconds. There we go. So now that makes a difference because now the instrument is no longer resetting the sweep it's doing. It's going to only reset every 10 seconds, and you can see that it's much more stable. The output is supposed to be 0 dBm, so let's do a peak search. There it is, and it is almost 0 dBm. There's some losses in the cable. And you know what? It doesn't look that bad. It's reasonable. It has some harmonics. It has some stuff, but the biggest harmonic is almost 40 dB below the fundamental that you're looking at. It's this one right over here. This is 10 dB per division. So you know what, at 1 GHz it doesn't look so bad. So let's go ahead and change the span. I'm going to do that peak search again. I'm going to send that to the center frequency, and I'm going to change the span so we can take a look at it. And you know what, I'd say that's not too bad at all. It's not a bad synthesizer. I'm going to go a peak search again. There it is. Obviously these are unlocked from each other. That's why you're seeing 998 and 99.8 megahertz. And you know, there's some tone over here, but again, that's almost 60 dB below to what you're looking at, and you can see the phase noise. But honestly, it looks pretty good. Let's do a peak search and go center span one more time, and let's change the span of the instrument again. There we go. Yeah, 10 megahertz to 50 megahertz span. Obviously now we're dealing with the phase noise of the unit, but I would say I'm pretty happy with that. If you want to have a synthesizer, it's not that bad for some basic experiments. Very nice. I have to say that they've made an improvement on their tracking generator. Of course, this is at 1 GHz, so let's look at what the signal looks like at all the way at the very end at 7.5 GHz. So let's try it at 7 GHz. All right, now I'm sweeping from 0 to 15 GHz, so we can see much more tones. So I'm going to go ahead and change the center frequency from 1 GHz to 7 GHz. And there it is. Here's a 7 GHz tone. I can do another peak search on it. There you go. Amplitude is -3, and look at that. It looks good. I have to say that this means to me, at least for a lot of applications, you should be able to use the Rigol DSA875. You know, for a crude synthesizer, it's not going to be perfect, but it's not going to be that bad. It's definitely going to help you in a lot of your applications. So pretty nice. Now that we know how this works, and by the way, I can change the amplitude. I want to make sure that I do everything that you might ask. So here's 0 dBm. I can go to -10 dBm. You can see it went to -12.5, which is perfect. Let's go to -20 dBm, -22.5. It's dead on, and all the way to -40 dBm. went to minus 42.5. It's perfect. It's almost dead on, and this is at obviously 7 gigahertz. It looks really good. My thumbs up for that. So let's go ahead and now hook it up to a circuit and do some measurement with it. And for the sake of completeness here, I'm measuring the phase noise of the DSA875. Now I'm doing that by applying a signal from the Keysight EXG synthesizer, and since that synthesizer has a much better phase noise than the Rigol internal synthesizer for the spectrum analyzer, I should be able to use it to measure the phase noise of this unit. So the 1 gigahertz signal that's coming in, and its amplitude is exactly 0 dBm, you can see right here in the middle of the screen, and I have a span of 1 megahertz and a resolution bandwidth of 1 kilohertz. I'm also using the built-in marker function of the instrument, so if you press marker function, you can select a couple of different things. Here I have a noise marker enabled that will give us noise power spectral density in dBm per hertz. But since the input amplitude directly is 0 dBm, I can read this value as dBc per hertz, essentially, which is what this would mean. This means that at a 100 kilohertz offset, the marker is at 1.0001 gigahertz. So at a 100 kilohertz offset from the carrier, the phase noise is minus 99 dBc per hertz, which is exactly what the datasheet says. So this is consistent at least at 1 gigahertz. And I'm not going to go through measuring every single one, but this gives you an idea of the shape of the phase noise and the internal phase noise performance of the instrument itself. This means that you cannot measure any source better than that using this instrument, because obviously it would be buried in the phase noise of the Rigol spectrum analyzer itself. But nonetheless, it matches the datasheet. Great. So let's move on. So the very first thing I want to measure is this amplifier, and this amplifier is a low noise amplifier which is supposed to work all the way up to about 8 gigahertz, and it can be used for broadband applications. You should have a very high gain at low frequencies, about 40 dB, just under 40, and the gain kind of goes down linearly in dB all the way up to 8 gig. So for a broadband application, this should be fairly interesting. Now let's imagine that you're working in a company and you're given this amplifier and someone tells you, yeah, there's some problem with the frequency response of this amplifier. Can you find out what is going on with it? So we want to measure its frequency response. Now this is powered using a micro USB here, so it needs 5 volts. So let's go ahead and power it on with that. But before we do that, we have to set up our instrument to measure frequency response. Now because it has a tracking generator, that's really straightforward. You can see that I have made a loop here. So this is going to be my input cable, this is going to be my output cable, and here's my through. The through here has very little loss, so afterwards when we remove it, it shouldn't have too much of an impact. So let's go on the tracking generator. I'm going to focus on the screen later. I just want to show you the routine here. So right now we can see the tracking generator level is by default minus 20 dBm. Now if this has a gain of 40 dB, we don't want to put 20 dBm in it, because that means that it will have to produce 20 dBm at its output in order to stay in the linear region, and it can't do that. So let's go ahead and reduce the power all the way down to minus 40. Now that's nice that this can go minus 40 exactly for these type of reasons. So because when this has 40 dB of gain with minus 40 dBm, it has to produce 0 dBm, which is about 650 something millivolt peak to peak, which is not too bad, into 50 ohm of course. So now that we have it, we can go ahead and turn on the tracking generator. Now as soon as we do that, we're going to get a flat line sitting at minus 40 dBm. That's exactly what should happen, because this is putting at minus 40 across the whole frequency. And look how nice and flat it is, even without calibration. That's one of the things I was pointing out when I was measuring the attenuation of the signal coming out of the synthesizer, and you can see how nice and predictable it is. So pretty happy with how flat this is, even at minus 40. Now if I were to increase it, of course, that line is going to move up. So if I put the line at, let's say, minus 10 dBm, you're going to get a flat minus 10 there. So no problem. Let's go back to minus 40, like that. And now we want to normalize this. So we'll click on normalize, and then we say, okay, well, give me a normalized vector. Now, as soon as you do that, it's going to give you a flat line at the very, very top. Now, of course, if you measure anything that has gain, it's going to go above the screen. That's not going to be very interesting. So let's bring it all the way down, let's say to 30%. There it is. So now we are ready for something that has quite a bit of gain. Whatever we measure is going to be above. Now if I were to go ahead and turn the tracking generator on and off, you can see the kind of dynamic range you can possibly get. When you put in minus 40 dBm at this resolution bandwidth, this is the dynamic range you're looking at, the line that is there and to the reference line that you have to find. So we know we have gain, so we have lots of dynamic range. We don't have to worry about that. I'm turning the tracking generator off so we can change the setup. Now I'm going to go ahead, remove our short, which is pretty straightforward, and I'm going to remove these protectors. I'm going to connect the output of this amplifier to our instrument, and the input of this amplifier to the tracking generator output. There it is. Nice, and it's perfect. So now obviously it's not powered on, so nothing's going to happen. Even if I turn the tracking generator on, all you're going to see is a tiny increase, and that's just through the leakage of through the circuit itself. So we can go ahead and power it on with our little micro USB cable over here, and if I can plug it in, that is, oh, still the wrong way. There it is, and look at that. That looks pretty good. So let's focus on the screen. And here is the frequency response of our amplifier. It looks pretty good. Let's turn on our marker. There we go. And I'm going to go under System, under Display, and I'm going to move the active function to the bottom so that those numbers don't interfere with what we are looking at. I'm going to go back to the marker. There it is. So you can see that at 3.75 gigahertz we have 27 dB of gain. Great. And I'm going to bring the marker further lower frequencies, all the way over here, so you can see at about 170, 160 megahertz we have 38 dB of gain, which is roughly what it's supposed to do. Now if you go any lower than that, it's going to drop really rapidly, and that's because there is this amplifier is AC coupled at its input and at its output, and that's the reason why you have that. But check it out, just like we said, there is indeed a problem in the frequency response of this amplifier, and there is a dip right here in the gain. At about 5.275 gigahertz we have a drop in the gain of the amplifier. Now this could be from multiple reasons. It could be that there is a resonance forming at the input or a resonance forming at the output, but clearly a problem in the matching network of the amplifier. Or if it's a multi-stage amplifier, a problem in the interstage matching. So this is going to be an issue if you want to use this for a broadband application, because you have now this drop in the gain. And if we can easily measure how much drop that is by selecting delta and moving the delta marker away. Let's say over here, you can see that, yeah, it's almost 10 dB, which is quite a lot actually. So there is a problem at 5.27 megahertz, and you can see how quickly we can find out by using this functionality. Is there anything else that I can measure using this tracking generator right away? Well, in fact I can, because I am able to adjust the output power of the tracking generator, and because the output power is pretty nicely linear in terms of the attenuation that is reporting, I can measure the output compression of this amplifier. And I can do that by first let's change the amplitude and make sure the reference level is higher, because we're going to now put more power into the amplifier. We want to make sure it can handle it. Let's go to 20 dBm reference level. Now we can go all the way up to 20 dBm. This amplifier can't produce that much, but nonetheless it will be a safe location. You can see that nothing changed by changing the reference, as it shouldn't in fact. Only a little bit of more noisy at the output because we are running closer to the noise of the instrument. I just increased the noise figure of the synthesizer of the spectrum analyzer by 20 dB by doing that. So let's go ahead under the tracking generator, and you can see that at minus 40 dBm we have a gain of 36 dB. So let's go on the tracking generator and let's go ahead and increase the gain, increase the input signal 1 dB at a time, and we will go until the output no longer changes by 1 dB. So we can see that the marker is right here, is 36 dB. The level coming in is minus 40. So let's go from minus 40 to minus 35. You can see that it went to 41, so it's still 1 to 1. So let's go 5 more dB. It went to 45.7, so it's getting a little bit closer. Let's go 5 more dB. There you go. And now we're almost a whole dB short. I would say it's roughly around here. We're about a dB short of where we're supposed to be. So going from minus 40 dBm, it gives you 36.1. Now if I go to minus 25, I expect 15 dB more, but I'm not getting quite 15 dB more. So that's roughly around where I would expect the 1 dB compression to be. So you can see that I can easily measure the 1 dB compression of the amplifier because I have control over a really wide range of output power from the tracking generator. More importantly, it's fairly predictable, and it actually does put out what it's reporting. So you can see how easily I can measure the compression. Now furthermore, I can also see very clearly that the compression happens earlier at lower frequencies, to be expected because we have much more gain there. So you can see as I further increase the power going into the system, the curve becomes more flat. And why is that? Well, it becomes more flat because what we're dealing with is that we are saturating the amplifier here, and we're operating in large signal here, and we're operating in small signal here. So this curve becoming more and more flat. If I continue, you can see that is now completely in a nonlinear form, and interestingly enough, we still have this resonance. And this is another piece of information that this test gives us. Because this resonance is there and it's so persistent, and since we're operating large signal now here too, I would say that it is likely that this problem is at the output of the amplifier's passive network, not at its input, again based on experience and so on. But you can see how much more flat this became. So now I have a large signal performance of the amplifier and not just its a small signal, all of it within one setup, within one measurement, because we have a tracking generator that has a very large dynamic range, allowing us to do this measurement. Fantastic. So it performs quite nicely here. So we identified several key parameters of this amplifier. We measured the amplifier's gain, we measured this notch frequency, we measured this frequency response, we found out what its input compression point, our output compression point is at a particular power and a particular frequency, and we measured its large signal performance all in one setup. Fantastic. So now I want to measure a different amplifier, and that's this one. And the reason I'm picking this is because there's a lot of interesting things that we can measure with this. This is a Wi-Fi extender amplifier. So this is supposed to connect to your router, and it's supposed to extend the range of your Wi-Fi router, meaning that it does that simply by amplifying the signal that's coming out of the router and amplifying the signal that's coming into the antenna in order to give you a little bit extra range. Now this is rated for 4 watts of output power, meaning a 6 dBm, which is a lot of power, and this can damage the input of this instrument easily if you're not careful, because again this is rated for only 20 dBm input. This is at 36, which is from 100 milliwatt to 4 watt. There's quite a bit of difference there. So we're going to investigate how this works. Now I've taken it apart the back, so I'm going to show you what it looks like on the inside, and then talk a little bit about this operation so we can devise a strategy on how to test and characterize it using the Rigol spectrum analyzer. So here's the internal circuitry of this amplifier, and as you know, Wi-Fi is a bidirectional system, meaning that it uses the same antenna port for transmitting and for receiving, and since it can do it simultaneously, it's a time division multiplex system. At least in most cases it doesn't do it from the same port. Now here we can follow the signal path, no pun intended, from the RF input to the RF output. Now the RF input is connected to the router and the RF output is connected to our antenna. So we would expect a PA driving the RF out, and we would expect a low noise receive path connected to this RF input over here. Now if you follow this, it's quite straightforward. We can see right at the very beginning, remember this port is the router port, right at the very beginning we see a passive signal splitter combiner. They can get away with using a passive circuit here because it's already after the amplifier, so it doesn't affect the noise figure. And then it goes through here, and you can see that the signal is after the splitter goes through this little path, and then it splits into two. There is another splitting happening, and then it goes into 2 power amplifiers operating in the ISM band, and then the output of those 2 power amplifiers are combined. I don't think this is a balanced amplifier structure. It looks like 0-degree phase, and then it combines them together, and then it goes through a pin diode selector switch, which then drives the output. Now you can also see some interesting again behavior here with the tapered transmission lines and so on, some matching networks along the way. Pretty cool to get 4 watts of power at 2.5 GHz in reasonably small form factor. And on the receive side, the signal is then switched with the pin diode to the receive path, going through this single path amplifier. Here's a transistor right there, going over there and then back onto the RF port. So something has to tell this pin diode switch whether to switch to this path or to this path, and to whether enable and disable the PAs and so on. And it has to do that as fast as it can, because at the time that it takes for it to switch is all dead zone. So what I want to measure? Well, I want to measure the response of the return path, and I want to measure how much power do I need to see at this port before this guy switches this amplifier to transmit mode. And it happens that there are lights on the other side which tell us about whether this is in transmit or receive mode, so we can easily find out, and that should be pretty interesting to see as well. So let's do something very basic just to see the return response first, and then we'll look at the transmitter. There we have to be careful because we don't want to damage the instrument. We have to put some attenuator. So it should be cool. Let's take a look. Here we go. I've already done everything. I've calibrated the instrument and I've hooked it up to the input and the output. So remember, this is the receive path we are measuring. So this is the low power path. This is the part that collects data from the air basically and puts it through an amplifier and then feeds it back onto your router. So I expect this to have reasonably low gain because the router itself already has a lot of gain. We don't expect a lot, but we do expect it to be centered in the ISM band. So let's take a look and see. I'm going to go ahead and plug this in. And check it out, we get the response and we see this light turn on, and this light indicates that the amplifier is now in receive mode and not in transmit mode. And so let me just make sure that this is properly tied in. I should be using a torque wrench, but anyhow, there it is. So let's take a look at the screen here and investigate a little bit the response of this amplifier, which is exactly what we would want to see. So I can enable the marker again, and you can see that indeed we have gain of about 9 dB, maybe 9.5 dB or so, centered at 2.45 GHz. I'm going to go ahead and switch that back up again by going under System, Display, and at the top. There you go, and marker. Yeah, you can see that at 2.45 GHz, right in the middle of where we want to be, we have about 9 or 10 dB of gain. Now, this amplifier, again, like I said, is in receive mode, and it is another interesting little feature in the response as well, although it's at minus 10 dB of gain, but we do have this little other blip over here. That's about minus 11 dB of gain at 1.33 GHz. And you can see that we can see the entire range of the signal there, and I can go ahead and put more power into it, and we should see no problem with this following, although I mean minus 40 dBm is quite a lot of power, because again this is supposed to be the wireless, but it should have a fairly good linearity. So let me go ahead to minus 30, and you can see that it says 20, so we still haven't hit the compression. It works reasonably well, no complaints. Now let's go and flip it to the other side and see what happens and how much power we need to put in order to get it to actually switch to transmit mode. So here's our setup again, except I flipped the amplifier over and I have added a 20 dB attenuator at the output of this, meaning that even if it puts out 35 dBm, the output is not going to exceed 15 dBm, and I don't believe it will put out that much anyway. So with 20 dBm of attenuation is more than enough. And to be further safe, we're going to go over here. I'm going to change the reference level all the way to 20 dBm, so we have 30 dB of front-end attenuation inside the instrument as well. And let's go and see what happens. I can go on the tracking generator, level at minus 40. I'm going to turn the tracking generator on, and guess what? Nothing happens, because at minus 40 dBm there isn't enough input signal being detected by the PA to switch it into transmit mode. You can see the red light is still on, so the signal is expected to flow in this direction, and there is nothing going on in that direction. Well, no problem. We have a tracking generator with a dynamic range at the output. We can go ahead and change that, and then we're going to go ahead and reach minus 30, and you can see still nothing. Let's go a little bit more, 20, and you're at minus 20 dBm, still nothing. Again, it's to be expected, because your router is going to put out more than minus 20 dBm, and that's how it knows when it should go into transmit mode. So let's go ahead and go to minus 10 dBm. Oh, we're beginning to see something. There you go, you can see the light's starting to blink. So we are beginning to be able to measure the sensitivity of the switching circuitry. So it turns out, let's go to minus 10, which is right at the edge. So minus 9 is over here. Now I can make a marker, and there you go, I just made a valuable measurement. It's telling me that at about 2.9 gigahertz or so, the sensitivity of the power detector at the input to switch to the transmit mode is about minus 9 dBm. Perfect. So let's go ahead and increase it further. 8, and you can see that we are in transmit mode for a larger portion of the frequency spectrum. Minus 2, minus 1, and 0, and that's the most I can do. I cannot go any higher than this with this tracking generator, and you can see that this thing is jumping back and forth between transmit and receive mode, because we are sweeping this entire range. Now if I go ahead under sweep and I change the time that the sweep takes, or I can just reduce the resolution bandwidth, it doesn't matter. There you go, at 100 kilohertz we're now sweeping about 749 milliseconds, and you can clearly see that this is jumping back and forth. So we just did some really valuable measurement just by doing that. And if I go under marker, if I measure the peak power here is a minus 7 dBm, you have to add 20 dB to that, so we have quite a bit of power coming out, but nowhere near where it's supposed to be, and that's because we are not able to saturate this amplifier right now with the tracking generator only operating at 0 dBm. But you can see clearly that in fact you can measure this type of unusual behavior using the tracking generator. So now the next thing I want to do is I want to put in some signal into this thing from an external synthesizer and drive it all the way to saturation, so we can measure its maximum output power coming out using this instrument. And then we're going to put in modulation signals and do a whole bunch of other extra characterization. But this is a pretty interesting little test to do with this unit. here we go. I have connected the amplifier to my Keysight synthesizer. I'm going to do all of my tests at 2.4 GHz. So the synthesizer is set to 2.4 GHz and 0 dBm of output power. We've already characterized how much power is required to switch the input, so we don't have to do that again. And we're going to go ahead and turn the output on, and there is our signal appearing. You can see that this thing switched to transmit mode, and I can go in peak, and then indeed we're putting out minus 10 dBm, and we have a 20 dB attenuation, so that's 10 dBm of total output power. Now I want to drive it harder and see if it can meet its advertised 4 watt 36 dBm output power. I doubt it, but let's give it a try. Let's go all the way another 10 dB more, and indeed it's putting out an extra 10 dB out. Now we are at 20 dBm, another 10 dB. Now we're at 8.8, so we're almost at 30, 28.8. We're gonna go another 5, 13 dBm. No, now it's saturated, it doesn't go up anymore. So I'm putting 25 dBm into it, and I'm getting 33 dBm out of it, which is okay. I mean, again, I don't think my router at least cannot provide that much power, so it cannot saturate it anyway, but this is how much power I can get. You can see the power is slowly dropping. That's because this is getting really, really hot. So this is a thermal effect that we are witnessing right here. And in fact, you can go ahead and you can put the instrument into zero span. So if I set the center frequency to 2.4 gigahertz, and I go ahead under span and I say zero span, now I have a curve as a function of time, and I can go under sweep time, and I can increase the sweep time to, let's say something like 2 seconds. Now it's sweeping every 2 seconds at a center frequency of 2.4 gigahertz and zero span. So if I disable the output, you can see that it comes down, enable the output, comes back up. So if I turn the output on and off, you can see the waveform that I can create with just by my hand, and you can see the light turning on and off on the amplifier. And you can use this trace versus time on a zero span, of course, to monitor things that are a function of time, like for example degradation, thermal degradation, or any other transient effect. Should be pretty interesting to capture. But anyhow, so let's go ahead and put some constellations into it, so we can use some of the built-in functions of the Rigol DSA875 to do some further characterization. So I'm interested in measuring the OIP3 of this amplifier, but before I can do that, I want to make sure that the OIP3 of the synthesizer is good enough to drive it. So let's go ahead and configure the synthesizer to generate a two-tone at 2.4 gigahertz, and take a look at it closely on the screen and see if that actually meets our requirement, and then use the internal function to measure the OIP3. So let's look at the synthesizer's performance before we move to the PA, and I have the synthesizer set to 2.4 gigahertz, putting out 20 dBm, 2 tones, 10 megahertz apart. So let's go and enable the output. There it is, and we can see that very nicely on the screen here with no problems. I have the marker right there at 2.4 gigahertz, and you can see that the LO feed through is about minus 48, minus 50 dBm, which is perfectly fine. Now here's our third order intermodulation products and our fundamental tones, and again for 20 dBm of output power, this is very good. Now I want to measure what the third order intercept or the output OIP3 is, and while we can always measure the powers, relative powers, and do a linear interpolation and actually find it out mathematically, is really straightforward, or we could use the function that's built into the unit. So let's go ahead and do that. We go under measure, and then we select the measurement. We have a whole bunch of measurement capabilities. We're going to take a look at a bunch of these, but first thing is TOI, third order intercept point, and we're going to enable that. Now the span is too small. When you jump on it, for some reason it changes the span. It should keep the span that you had in your spectral measurement. I don't know why it does this, but anyhow, that's easy to fix. We go under span, so it cannot find the two tones. That's why it's giving us that warning. Let's go ahead and increase the span until the two tones come into display, and there you go, the warning will go away. And look at it, it looks very nice. It's very, very easy to use, and you can see I can also go ahead and enable the marker, so we can see here's our first marker, here's the two fundamental tones that it has automatically detected, and here's are the intermodulation products. So you can see it tells you that the bass lower, the bass upper are at 2.395, 2.405, and the third order upper and lower sidebands are at 2.385, 2.415. So it gives you the power of all of these, and it's telling you the DBC, the ratio of the fundamental to the intercept points, to the intermodulation. You can see that's minus 50, which is quite good. Remember, it's 20 dBm putting out from the synthesizer. Minus 50 is pretty amazing, and it gives us an OIP3 of almost 40 dBm, which is great, which means that it is almost a guarantee that the amplifier we're going to use is going to degrade the signal for sure. So we are not limited by our synthesizer, and this quick test verifies that. So the next step is to now take our amplifier and put our amplifier here instead of this through, and then we can see how much the OIP3 has actually degraded from this measurement. So should be very cool to see. And here's the amplifier in the middle, everything exactly the same. Remember that there's a 20 dB attenuation there. I haven't changed the synthesizer settings, and we can go ahead and enable that. And voila, it switches to transmit mode, and now we have all of our individual tones. Let's take a closer look at that. And to be expected, our intermodulation products have degraded with respect to the fundamental tone. You can see them in dBc, so they went from -50 to -34, so this amplifier does add some nonlinearity. But something else that I forgot to mention before is that it actually gives you the dBc of the two tones, which can be very useful. You would expect these two tones to have identical amplitude, but they usually don't have exactly the same. So it takes the highest one and sets that to be your zero reference, and it tells you, or in this case actually it's taken the first one to be your reference, and then you can see that it tells you, oh, the other one is 0.2 dB higher. So it's very useful to have all of the values right in front of you. The dBc values of course don't get scaled by the fact that we have attenuator, but you can see that the relative value has degraded, but the output intercept point, it is actually 21.2 plus the 20 dB attenuator, so it's 40, almost 42 dBm. So it is a fairly good amplifier. It can do a nice job, and the reason the OIP3 hasn't degraded so much is because obviously there's some gain in it, but even though the intermodulation products have degraded, so it's pretty nice. And now what we can do is with this information in hand, we can go ahead and put inside this amplifier a real modulated signal, and with that we should be able to easily find out this performance and use other measurements that are built into the spectrum analyzer to get a better idea of its performance. So one other small thing I wanted to mention is that we measured the gain of this amplifier before in transmit mode, and the gain was about 10 dB, and we can use that measurement in combination with the measurement we have now to calculate the input third order intercept. So we know that, for example, we are actually right now, because it has heated up so much, that the OIP3 has dropped to 20 plus 20, it's about 40 now. So we gain is 10, so that means that the third order intercept point at the input is 30 dBm, which is very, very high, but that's to be expected because this is a passive splitter at the input and so on. It has very little gain, so it's supposed to have quite a high input third order intercept point, but nonetheless pretty important and an interesting measurement. Let's go. So now let's go ahead and put an actual modulated signal into this amplifier and see how it behaves. So I've configured the transmitter, the synthesizer again. This time is putting out 50 megasymbols per second, 64 QAM constellation at a center carrier frequency of 2.4 gigahertz. The output power is the same, 20 dBm. So I'm going to go ahead and enable it and take a look. We can see that if we're jumping back to transmit mode again, as to be expected, and we can see a very nice constellation spectrum there, and you can see the adjacent channels due to the limited OIP3 of this amplifier. We're polluting the adjacent channels, and I just want to know how badly we are actually polluting it. Well, we can do a whole bunch of measurements on this spectrum with built-in functions into the DSA875. So let's take a look at that. So let's first verify we're indeed looking at a 2.4 gigahertz carrier, and if I enable the marker, indeed you can see that we're at 2.4 gigahertz. So I want to find out how much bandwidth I'm occupying, and that's really easy to do because there's a function built in there for you. And if I go under measurement and under selection, we have channel occupied bandwidth, and let's select occupied bandwidth, and then the screen comes up and you're able to configure this function with the total power ratio, and this power ratio is telling the instrument how much of the overall power you want to capture in your channel in order for it to calculate the occupied bandwidth. So I've said 99%, meaning tell me a channel size where 99% of my transmitted power is contained within it. And it does that calculation for us, and it says your occupied bandwidth is about 63.5, let's say 65 megahertz altogether, which is not so bad, and it makes sense because we're doing 50 megasamples per second, and we have a root raised cosine pulse shaping with a coefficient of 0.5, and that means that we don't have quite a Nyquist pulse shaping, so we are occupying more bandwidth than our baud rate, and that's perfectly acceptable. And we can see that it also tells us the transmit frequency error of about a couple of hundred kilohertz up and down. That's because these two units are unsynced. They don't have a 10 megahertz at the back connected to each other, so this is a free running synthesizer compared to with respect to the other one. That's why you have this issue. So other than that, it's very straightforward, very easy to use. There's really not that many functionalities built into it other than that, and it works quite well. I'm pretty happy with it. So now that we know the occupied bandwidth, we can use that information and actually find out how much power we are transmitting. So if I go under measurement, instead of occupied bandwidth, I'm going to select channel power instead. And under channel power, now that I know what my channel width is, I can go under measurement setup and I can say integrated bandwidth of 65 megahertz. That's my channel size. And now it's telling me that within your channel, you have about 12 dBm of power. And remember, there's a 20 dB attenuator, so we are transmitting a total of 33 dBm, which is great. It's about 2 watts, which is perfect. Now, the power spectral density says it's minus 66 dBm per hertz. That's the power spectral density of the constellation, and that's a function of the fact that this is a 64 QAM constellation and so on, with the baud rate and so on. So it all makes sense, and these are all really important measurements. What if I want to know other things that are important? For example, I want to know what is the ratio of the power that I'm occupying in my channel with respect to the ratio of the power that I'm emitting in someone else's channel. Remember, in wireless transmission, especially in Wi-Fi, you don't want to occupy someone else's channel. That's actually illegal. So if you have a very nonlinear amplifier and it's generating these side lobes which are larger than you're allowed to have them, you're occupying someone else's spectrum, and now they have to be able to ignore your signal. So the adjacent channel power measurement is a critical wireless application measurement unit. So that's why it's included as one of the fundamental measurements in here. So if I go ahead and select the adjacent channel power, now I can configure the instrument with what my own channel bandwidth is and how much adjacent channel bandwidth I want to consider, and it's going to give me a ratio of the two powers within that. So what I have done is I have selected my own channel bandwidth to be 75 megahertz. Let's say the channel that I'm allowed to use is a 75 megahertz channel, and I want to know how much power I'm emitting in someone else's spectrum at 50 megahertz away from me. So let's go ahead and increase the span a little bit so we can see better what's going on. So this is my channel, this is someone else's channel, and that is someone else's channel, and I'm putting power in them, which I shouldn't be. I am in my own channel, I have 12 dBm plus 20, so 33 dBm, and then the upper and lower sidebands are at minus 23 dBm. So it's actually about with the attenuation, I'm almost at zero. I'm at about minus 3 or 4 dBm power. Now the ratio of those is minus 36 dBc. So I'm transmitting 36 dB and more power than I am putting in the adjacent channel. Whether that's acceptable or not depends on the wireless link and depends on the regulations and rules and FCC regulations and so on and on. So it's a very, very important measurement, and it's built in here, and it's quite easy to use. I'm pretty happy with it. There's a couple of other things you can measure. For example, the effective bandwidth, where you can tell it a specific dB value. There is transmit power. There is as well. There's also a carrier to noise ratio. These are really straightforward measurements, and you can go. I don't want to go into too much detail so that I don't continue talking about the same thing. I want to do some other measurements here for you, but you can see that these are all built into here. Another measurement that we have, we already used the TOI. There's a harmonic distortion. I'll talk about that separately with a different experiment that I have, but overall I think it works rather well, and the functions are all nice. Now up to this point we have completely characterized this amplifier from a whole array of its functionality. I'm still going to measure its input and output return loss, but we're going to do that next. But one of the things this unit doesn't have, which I wish it did, is it doesn't have a digital baseband built into it. So it doesn't have a digital analysis bandwidth where it can demodulate for you or give you I and Q information, and there's a whole world of different type of measurements you can do once you have access to a digital baseband. As you have seen in some of the other spectrum analyzers that I have reviewed, this is something that I believe Rigol should easily be able to implement because they have all the technology required. They make oscilloscopes, they make arbitrary function generators, they make spectrum analyzers, so they really know how to do this. It's just a matter of implementing it. And of course writing the software for it, which is really, really important too. So that's one thing that's missing. I wish if it had that, I mean, it'd be game over. Nothing would even come close to competing with it in its price band. So I hope that's something that they add to it in the future. It's a hardware change, of course, but from everything else, so far, pretty good. Let's go do some return loss measurements. We can also measure the linearity of a broadband amplifier by measuring its THD. And this can be pretty useful if you're dealing with something that's occupying quite a lot of bandwidth. And since this is a broadband amplifier, we can definitely do this type of measurement on it. And I'm going to apply an RF signal from this port and just measure directly the RF output port of this amplifier here. And we're going to use the application built into the spectrum analyzer to measure the THD. Now I'm going to apply a 2.4 gigahertz signal, and normally when your spectrum analyzer stops at 6 gigahertz, you're not going to be able to see the third harmonic of a 2.4 gigahertz signal. But because this specific spectrum analyzer goes all the way up to 7.5 gigahertz, it gives us the advantage of being able to actually see all the way up to the third harmonic. So let's go and enable the signal. And there you go. And you can see our fundamental tone, our second harmonic, and all the way at the end our third harmonic where my marker is. Now if I want to measure the THD of this, obviously this THD is going to depend on the input signal power. So if I were to go ahead and increase the signal power, you can see that the tones will come up as to be expected. And you can see the third and the second and the third harmonic. Now remember that in theory you're supposed to de-embed the losses of the cable and the losses of because the loss here is also frequency dependent, not to mention the amplifier gain is also frequency dependent. But anyhow, aside from that, this is normal behavior. So let's go ahead back to -30 and let's enable the application and take a look and see how it performs. So to measure THD, we will simply go under measure and select from the function list all the way at the top the harmonic distortion. And what this will do is it will identify the largest tone and it will pick that as our fundamental, and it will look at all the harmonics, and it will dwell at each different harmonic for a certain duration of time to measure the power at that harmonic. So let me go ahead and turn the marker off because we don't really need it. And if I go under measurement setup, you can see that I can change what the dwell time on each harmonic is. Right now it's set to 750 millisecond. I can change that to, let's say, 100 millisecond or so, like that, and you can see that it would jump much faster between each of the harmonics and at different power levels because each harmonic has a different level. You can see here, for example, that it's giving us the total THD, which is 0.63%, and it has found 3 harmonics, and the sweep time is 100 millisecond, and the harmonics are written here: 2.4 gigahertz, 4.8 gigahertz, and 7.2 gigahertz, and the relative power, no, actually the absolute power of all the tones are given. So if I go ahead and increase the power into the amplifier, our THD is going to degrade because our harmonics are going to come up faster than the fundamental grows, and we're going to go ahead by 5 more dB. Let's actually go all the way to -20 dBm. So if I do that, now you can see that we have quite a bit much more THD. Now we at 5.33%. Our output power is almost 10 dBm, 9 dBm, and our second harmonic, our dominant harmonic, is -18, and the third is -20. So you can see it's really easy and straightforward to do very quickly a THD measurement. This can be quite convenient when you are dealing with broadband circuits and that you want to do some quick measurements. So I'm pretty happy with these applications. I wish they would develop more of these and you know, put them into the future versions of the firmware because they're quite useful. Now I also want to get the computer interface to this unit working so we can look at the Ultra Spectrum, which is a separate software. It's at $250 or so, which allows you to create all kind of spectral measurements and waterfall measurements and so on. I'll take a look and see if I can get that to work on my computer. We'll take a look at that as well. And here's a look at the Ultra Spectrum, which works with the DSA875. As I said, this is a software you have to purchase. It's about $250, but it does come with a 15-day trial, so you can try it out before you decide to buy it. Right now I'm here on the basic view of the software, and I have to say I had to install and uninstall it many times. That includes with Ultra Sigma. They both crash constantly. If I try to move this window by dragging it over, it will crash, and so I'm a little bit afraid of clicking in different places. These software bugs should be fixed. I mean, it really doesn't take much effort to fix these things, and then you can have a much more powerful offer for the customers, because these softwares are very important. All the competitors, especially the big competitors like Keysight, Tektronix, and so on, they make really nice software. So anyhow, going back to this, you can see the basic view. One of the things I really like about it is that if you hover the mouse over different settings, it will tell you all the parameters associated with that particular setting. That's very useful, especially if you're not very familiar. So for example, if you go under peak, you can see that's the detector type, so you can then select your detector type based on that. One of the things that's a bit annoying is that it doesn't go away once you move away from the button. So if you have multiple things stacked up, it kind of blocks your view. You have to click somewhere else for it to go away. And you can also go on the base and you can go on the advanced and it give you all the more advanced function. So let's go ahead and recenter this. The center is right now 3.75 gigahertz. Let's center it back to 2.4 gig. And let's change the span to 100 megahertz. And let's go ahead and change the resolution bandwidth to 100 kilohertz. So you can see that we have a spectrum again, we have a modulation centered at 2.4, and if you pay close attention to this area, you can see all these extra tones come and go. And that's because the amplifier that I'm using is not very well isolated, and is actually picking up other ISM band signals that are in the air, which is quite unfortunate because it means that it doesn't have good isolation, probably through the USB port where it's being powered. So if I want to look at that on a waterfall, I can actually do that, and I can go ahead and enable the recorder. And you can see, oh, let me get rid of that. You can see over here the waterfall is showing the peak, which is right this area. You can see it in bright green, and the spurious tones that appear and go show up as this discoloration here on the waterfall spectrum. So this can be pretty useful, showing you the randomness nature of it. And over here there is this unusual little 3D plot which you can rotate around, and well, I guess it could be useful under some conditions. So if you look at it dead on, for example, here, you can see indeed that there is some buildup of tones that you don't want. It's actually quite difficult to use. There it is. You can see these tones that I don't want versus time. Those are the spurious tones that come and go. The other thing that's nice is that every single functionality that I showed, all the different measurements, they're all accessible through here, built into here. So you can go and enable, channel power, occupy bandwidth, the TOI and transmit power. All of them are over here, as well as the correction you can apply if you're using the tracking generator and so on. So everything is really nicely built into this. If they put a bit of effort and fix it, I think it would be really worthwhile. It can be a nice software. I'm tough on it because it's not free. It's $250, and that's not, that's quite a bit of money. For $250, almost $300, you can buy an oscilloscope from them. So yeah, they have to work on this in order for me to be able to be kind of happy with it. But other than that, I like the way they've gone with it. I think they have a very good start, a little bit of effort, and then that'll definitely be something that anyone can use. Of course, this is all using Skippy language, so you can program your own and grab data, but they've done a nice job here. And I just wanted to give you a quick idea that this is available, and that give it a 15-day trial, download it and play around with it, see, maybe it doesn't crash, it's not as unstable on your computer, but I tried everything, and this is the best that I could get out of it. Alright, that's just a quick view, let's move on. Well, there is so much more that I can talk about here, but this video is getting longer and longer. There's a lot of functionality that I still haven't shown you. It obviously has demodulation capability, and it can do AM and FM demodulation. As I said, it doesn't have the digital processor in it, so it can't do proper INQ, but basic demodulation it is capable of. You can of course take screenshots, capture things, and do all the basic things as you would expect from a spectrum analyzer. But I just wanted to give you a reasonably in-depth look at its performance and look at some of its main functionality. I would say overall I'm pretty happy with it. It really, these type of instruments put pressure on the big brand names because they offer you so much with a reasonably little amount of money. For a 7.5 gigahertz spectrum analyzer with all the capability that's built into it and a tracking generator, a price of less than $10,000 is pretty amazing. I mean, this would have been unthinkable a couple of years ago. So I would say I'm pretty happy with it. It does have some of its limitations, obviously, in terms of some of its critical parameters like phase noise and displayed average noise level and so on. If you want to improve upon this, then you really have to go to the competitor, in which the price then goes up by several factors over. So if you, for basic measurements and just general use spectrum analyzer, I think it's a pretty nice unit. And if you liked this video, leave a comment for a discussion, give it a thumbs up if you enjoyed it. And if you happen to purchase one of these from Rigol because you saw this review, let them know, because it helps me have a good relationship with the manufacturer to be able to bring you other reviews in the future. Of course, I don't get paid for any of these reviews, and it makes no difference. I don't get any of the sales portions or anything like that. It's just so that I can have a good relationship with them. So if you enjoyed it, let me know. Until next time.